Good morning, my dear JEE 2025 warriors. The time has come for the next session of your NTA revenge. It's time to challenge NTA because NTA put good questions for us, and we cannot sit back, relax, enjoy. Obviously, we have to up our game. And if you're not on the top of your game, guys, you are already falling behind, not by hundreds of rank or even thousands, but by tens and tens of thousands. So gear up, my dear J warriors, because the entire nation has gathered to study for the April attempt, and you cannot be led behind, or else your rank will be significantly affected in the April attempt. So it's time to do KTG Thermo, one of the high weightage topics which was seen in your January attempt. Yes, it was also an important topic even in the pre-COVID era or even during the COVID era, but this was one of the very important topics. So let's go with the concept questions. Concept questions. That's how the lecture is going to proceed with your captain Shreyas. Good morning, Janvi, Ayanshu. I am very good. Thank you for all the love from Tamil Nadu, Jeffrey. Hi Akil, hi Nikhil, nice to see you back. Hi Jayvant, nice to see you Nikhilesh. Welcome Rockstar, nice to see you back. Username is unknown. Oh my god. Hi Jarvis, hi Chinnu, Prakash, Harish, Adi, Santosh. Welcome Panda, welcome Tanushika. Good morning, my dear warriors. Yes, I'm starting this chapter by today only, Harish. No issues. What you should do is please make sure that whatever classes you guys have missed, I'm telling you, they are very important. This modern physics was a very important unit, guys. I mean, so many questions. I have also taken care of, by the way, semiconductors, logic gates in the same session. It's a big session, 2 hours class, in a very concise, so that you will revise completely very quickly. Okay. So please go through that. And also, of course, the lecture before that was ray optics, heavy weightage. Maximum questions in January attempt were from ray optics. Obviously, you have your maths and chemistry also. Go through those lectures. Every lecture, try to go it at 2x speed. Yeah, because if you have missed it, you have to make up for it at a faster pace. Okay, I hope you have liked the video. Yeah, have you liked the video or not? Yeah, like it right now and subscribe to the channel. Thank you for subscribing. Yeah, great. So let's begin. Let's begin. The flow of the topics, I mean, the topics that we'll be covering in this particular class will be KTG, law of equipartition of energy, the ideal gas equation, the speeds, the Maxwell distribution, mean free path, the specific heat capacities, the degrees of freedom concepts, then obviously the thermodynamic laws, the thermodynamic processes, the work done heat, internal energy for different things, cyclic processes, all these things in today's class. Starting off with the concept of mean free path. Great, you guys have liked it. Oh, Kadappa, Nikhilesh, that's great. Nice to see you. Many of my very old relatives are from Kadapa. Okay, so starting off with the mean free path. Now look at this. This is just a gas chamber. Okay, and these molecules are moving around randomly, colliding with each other with different speeds, different energies at a certain temperature. I can heat it or cool it. As you can see, you concentrate on any molecule, it goes collides. There is some distance which any molecule travels before hitting it, and those distances may sometimes be very short or very long. If you take an average of all the distances of all the molecules, not just a molecule, if you take the average distance that a molecule travels, it travels 1 meter, 2 meters, 1.5 meters, 0.5 meters, 0.3 meters, like that. Of all the molecules, that average distance which the molecules travel between successive collisions is a straight line. That distance, average distance, is called as the average free path or the mean free path. Is that clear, my dear students? Is that absolutely clear? So if the molecules keep colliding like this and they keep traveling like this, so these are the successive collisions. So the mean free path is nothing but your average distance between between successive successive collisions, and this particular mean free path, lambda bar, lambda average, whatever you want to call it, is don't think of it this style of vector. Sometimes people just call it lambda average also. is proportional to the volume of the gas. If the volume is more space, so you will travel more freely, easily you will be able to travel. So it is proportional to the volume. It is inversely proportional to the number of molecules, because if there are more molecules in the same space, it is crowded. So the distance that you travel will be less. It's like a crowded railway station. More the crowd, the lesser free distance that you get. So it is inversely related to that. There are some constants which come over here, and there is also d square here. Basically, this d is the diameter of those molecules. Diameter of those molecules. So this is basically your d. This n stands for the number of molecules. Number of molecules, which you can also write it as number of moles into Avogadro's number. This n is nothing but the number of moles. This Na we all know is 6 into 10 to the power 23. This is obviously your volume, not velocity. Be careful. Okay, this is nothing but your volume. Shall we do some questions on this? Oh, no problem. You can watch it at 2x later on also. Great. So let's solve some questions. Here is your first question, which is a statement-based question. Read it carefully. The mean free path of molecules is inversely related to the square of the molecular diameter. The average kinetic energy of the molecules is proportional to the absolute temperature of the gas. Which of them are correct? It's not even assertion reason, it's just which of them are the correct statements. I'll just move aside. Quickly mark the correct answer, guys. Everyone, these kind of questions, very straightforward. You should be easily be able to do it. Hi, Rockstar. Degree of freedom is your favorite. Yes, it's a very interesting concept actually. Come on, come on, come on, my dear warriors. Everybody spam the answers. Don't be mute spectators. Everybody spam the answers. What do you think the mean free path is inversely proportional to the molecular distance? Yes, definitely. The mean free path definitely is inversely proportional to the molecular diameter square. That is true. Average kinetic energy of the gas. Yes, if you increase the temperature, the average kinetic energy directly goes up. This is also true. If the temperature is less, then the molecules will not move so randomly and so frequently. No more, not so frequent collisions, not so high speeds. Their speeds also will reduce. So the kinetic energy will increase if temperature increases. Temperature decreases, kinetic energy decreases. There is a direct relationship between the two. Yes, so both statements are correct. So B for IIT Bombay. Excellent. Yeah. Yes, both are correct. Very good. In fact, within some time, we will see the exact relation of the kinetic energy and temperature. For those of you who are aware and of that chapter, this kinetic energy is measured by internal energy, and it is given by the formula NCV into T. As you can see, it is directly proportional to the temperature. CV is the molar specific heat capacity at constant volume. N is nothing but the number of moles. So you can see it is directly proportional. Moving on, if n is the number density, d is the diameter of the molecule, then the average distance covered by the molecule between two successive collisions is how much? Come on, my dear students. Come on, my dear students. How are you going to do this question? If n is the number density, see, we know that the average distance is nothing but volume divided by root 2 times pi d square into the number of molecules. How about taking the volume below? So it will become 1 by root 2 pi d square into 1 by n by v. Now, what is this n by v technically? What is this n by v? Number of molecules per unit volume. So I can just call it as number density. So I can just call it as the number density. If it was mass density, it will be mass per unit volume. This is number density. Rho is the symbol for density. This is number wise density. So definitely that should be the answer. So if the n is the number density, d is the diameter of the molecule, then the average value will be how much? So you can use rho n, or you can also use small n as the symbol. In this case, they have used small n as the number density. Small n as the number density. So definitely this is the answer, guys, which is nothing but your option number. Yes, A. Perfect. Yeah, correct. Root 2 pi n d square. Root 2 pi n d square. It is not going to be n square. Yeah, option A, perfect. Thank you, Anand, for all the love from Kerala. Means a lot. Means a lot. We have a lot of students specifically from Kerala because there is not even one channel which is doing work for JEE students in South India, specifically for Kerala. And I see the analytics, and a lot of students in Kerala love it. And I keep reading your comments. Thank you guys so much for all the love. Now, there was one more question, guys, which came before I go to the next topic. This also can come. They might ask you in a question, they can ask you in a question, what is the average frequency of collisions? What is the average frequency of collisions? These kind of questions can also come. So when such questions come, look at it, how you are going to solve. The average frequency of collision will be the average time between the collisions inverse value. Just like in current electricity, you have these electrons which keep colliding with each other, and there is something called as recession time. This average time between the collisions is a very similar concept to the one you have learnt in current electricity. Now, this average time, I can say time is distance by speed. So it will be nothing but the average speed. Now, what is the average distance between the collisions? That is basically your lambda average. And on the top, you will get basically the average speed. This is nothing but your mean free path. This is nothing but your mean free path. This is nothing but your mean free path. Is that okay? So, if time is asked, it will be distance by speed. That means it will be lambda by v. If frequency is asked, it will be exactly opposite. It will be v by lambda, average. Is that okay, everyone? Awesome. Great, great. Now, you might be wondering, what the hell is this average speed? What is the formula? Sir, I forgot. Don't worry. I'm going to revise everything for you. So, before we see those formulas, let's quickly revise the ideal gas equation, which we all know is nothing but PV is equal to nRT, where P is your pressure, V is your volume, N is the number of moles, N is obviously your number of moles, is the number of moles. There are different ways in which I can write it, like I can write it as N by Na. Na is the Avogadro number, which is 6 into 10 to the power 23. N is the number of molecules. You can also write it as the mass of the gas, upon the molar mass of the gas. So this M stands for your molar mass. So that also can give you the moles. For example, if 32 grams of oxygen is present, so molar mass is 32 and mass of the gas is also 32. So 32 by 32 is 1. If 64 grams is present of oxygen, that means 2 moles of oxygen is present. So that's how also you can write the moles. There is another way of writing the same equation, which is pressure into molar mass is equal to density into density into RT. Yeah, this is also another way of writing the same formula. Okay, here M is your same molar mass, rho is nothing but density, R is your gas constant, T is your temperature. Sometimes density related questions can be solved using this equation. Next, this particular equation, very, very important, guys. PV is equal to 1/3 Nm V square. This comes by the assumptions of KTG. Yeah, these equations come from, this is your KTG, pressure versus speed relationship, which comes from the assumptions of the kinetic theory of gases. There are a couple of assumptions at the start of the chapter. It's there in NCERT, like the molecules move randomly, the speeds are different, the size of the molecules are very small as compared to the container, most of the space is empty, then the collisions are elastic in nature. The collisions, when occur on the surfaces of the container, they impart forces and impulses that gives the pressure of the gas. As the temperature increases, the randomness, the motion, the speeds increases, thereby the kinetic energy of the gases also increase. All these things are there at the start of the chapter. Just have a look at it. Okay, so P, pressure into volume, is 1/3. N is your same N, number of molecules. This M over here, though, this small m over here, is nothing but the mass of a molecule. This is mass of a molecule, not the entire gas. Yes, the mass of a molecule. And the mass of a molecule, please remember, it's the molar mass. Capital M is your molar mass divided by Avogadro number. Divided by Avogadro number. Obviously, if 32 grams is there in a mole and a mole contains 6 10 to the power 23 molecules. So for each molecule, you divide by the Avogadro number, you will get the mass of each molecule. Okay, this is again very important. Yep. Shall we go ahead? Yep. Okay. Let's go. Let's go. Let's go. Let's go to the next one. So, by the way, you can also rearrange this, guys. If you take number of molecules into mass, what will you get? Come on, guys. N into small m. Put it up in the chat box quickly. What do you exactly get? If I multiply n into m, what is it that you are going to get? This will be what? Yes, perfect. The total mass of the gas. The total mass of the gas. If I take volume below this, if I take volume below this, if I take volume below this, what will this entire ratio give me? What will this entire ratio give me? Mass of the gas by the total volume. Yes, it will just give me the density of the gas. Exactly, the density of that gas is what I'm going to get. So that's why you can see this equation comes. If you take volume below, so pressure will be 1 by 3 density into RMS speed square. Exactly. Very good. Oh, so what is this? What is this term over here, which is over here? Yeah, this particular thing. That is nothing but your root mean square speed. Yeah, root mean square speed whole square. Correct. So that is what that is. Okay. So no, this is not needed. Now coming to the speed relationships quickly. So remember, all the molecules do not have the same speed. In fact, you can see over here, some molecules are very slow. Suddenly, when they collide with some energetic molecule, they get very high speed. So there is a speed graph which you can draw. See this. I don't know whether you are able to see it properly. The speeds which are very low are very less. The speeds which are very high are also very less. Majority of the molecules have a certain range of speeds. This is number of molecules on the y-axis. On the x-axis, it is the speed. If I heat the gas, immediately you will see the graph shifts. The molecules start getting more and more energy. The temperature is increasing. Do you see the graph is going to slide towards your right-hand side? As you can see, as you heat it, many molecules will start getting higher and higher velocities. So you can see the graph is slowly shifting. Higher speeds are now being obtained by newer molecules, and you will see majority of the chunk of the molecules will now get more speeds. Yes, you can see they will go at higher speeds right now. If I cool it, obviously the entire graph will shift towards the left. This kind of distribution was given by whom, guys? Come on, name the scientist in the chat box. As you can see, I'm cooling it and the graph is shifting towards the left side. What is this called? Yes, it is called as Maxwell speed distribution. Correct. So Maxwell speed distribution, Maxwell speed distribution, guys, where you will see that if you draw speed on the x-axis and the number of molecules on the x-axis, that particular graph will be like this, and this particular peak happens where you should get something called as the most probable speed. This is the most likely or most probable speed. Yes, the most probable speed, most likely speed. Many molecules have that speed, so that is why that peak is there. The speed formula for most probable, for the most probable speed is nothing but root of 2 times of RT divided by molecular mass. Yes, root 2 RT by M. Similarly, there is also a formula for average speed. Average speed. The formula is 8RT divided by pi m. Do not forget what average is. Average is speed 1, speed 2, speed 3, like that. N molecules are there, so nth speed divided by the number of molecules. Lastly, you have the root mean square speed. The formula for that, the same root mean square which I used over here, RMS is 3RT divided by the molecular mass. And remember, RMS is where you take the squares of the speeds first, V1 square, V2 square, Vn square. Then you take the mean. Mean means you take the average of it. And finally, you take the root of that. That is your root mean square speed. Is that okay? Shall we do some questions now? Shall we do some questions? Before going to the questions, can you quickly tell me, out of RMS, average, and most probable, who is the highest and who is the lowest? Who is the highest and who is the lowest out of these three speeds? Quickly in the chat box, everybody spam the answers. Out of RMS, average, and the most probable. Everyone, come on. Everyone. Yes, VRMS is the highest because see, RT by M, RT by M, RT by M, same. So this number 3 is the highest number. The smallest number is the number 2. You're like, sir, what about 8 by pi? Pi is 3.14. If you divide 8 with or 9 with 3, obviously it will be 3. But 8 by 3 will be less than 3. But it will be more than 2. So this 8 by pi number is slightly more than 2, but slightly less than 3. So hence it will be between these two numbers. So out of these three, obviously, this is the least value for a given temperature for a given gas. This is the maximum value. This is the maximum value for a given mass for a given temperature. Great. Awesome. Let's do questions, guys, on your screen. When you change the pressure of a gas, the volume falls off more rapidly in isothermal process. Oh, wait a minute, this should have come later on. Not now. Sorry, guys. Not now. We'll do processes first and then we'll come. I don't know why these questions came over here. Sorry, we'll come to that in a bit. This were the questions. My bad. We'll just star mark it so that we know we have to come back. Just 1 second. I'll just star mark it. Okay, so we'll come back to these questions. The actual question was here. Okay, the ratio of vapor densities of two gases at the same temperature is 4 by 25. Then the ratio of the RMS velocities are, the ratio of the densities are this and this. What do you think is the ratio of the RMS speeds? Come on, the options are visible, I hope. Yes, 5 by 2, 25 by 4, 4 by 25, 2 by 5. One of them is the correct answer. Come on, my dear students. Which one do you think is the correct answer? Yep. There is a direct relationship. I just showed it to you. The vapor densities of two gases at the same temperature is so and so. Ratio of their RMS speeds will be, okay, many people are saying D option. Is that so? We'll figure it out. See, guys, pressure is equal to 1 by 3 density into RMS speed square. I just showed this particular equation to you just some time back. So the ratio of the vapor densities at the same temperature is proportional to what, guys? Can you see that RMS speed square is inversely proportional to the density? Is inversely proportional to the density, or yeah, or I can just take the root of it also. So RMS speed will be inversely proportional to 1 by root of density. So the RMS speed ratio, that means VRMS1 by VRMS2, will be nothing but rho 2 by rho 1. Yes, inversely related. So rho 2 by rho 1 will come. So it is clearly mentioned this is 4 by 25. This is basically mentioned 4 by 25. So this will be nothing but rho 2 by rho 1 will be 25 by 4. 25 by 4's root, which is nothing but 5 divided by 2. So that is the ratio of the RMS speeds. So hence the answer should be A, guys. No, some of you said D initially. Be careful. Yeah, it is option A. Very good, Praveen. Awesome. Jayant. Yes, Ivan. Yes, Jarvis. Very good. Hello, Arigato. Hello, everyone. Very good, Abhirami. Nice to see you back, guys. and keep answering the questions. It's very important for you guys, not for me. I have cleared my JEE more than 15, 18. Oh my God, it's a long time, guys. It's almost 20 years I cleared my JEE. Oh my God, that's a long time. Anyways, for a particular ideal gas, which of the following graphs represents the variation of the mean square velocity of the gas molecules with the temperature? Direct question, Maxwell speed distribution, guys. Everybody answer the question. Yep. Which of the following graphs represent the variation of the mean squared velocity of the gas molecules with the temperature? But they have asked versus temperature, how the graph looks like. Versus temperature. Versus temperature. How does the speeds look like? Okay. I just showed you the formula of RMS speed, and it was root of 3 RT divided by M. Well, the mean squared velocity of the gas molecules with the temperature. Be very careful. Many students are going to say, sir, can you see, sir, Vrms square is proportional to temperature. So it has to be a parabola. It has to be a parabola. Correct. So either it will be this or it will be this. Either it will be this or it will be this, but it is the squared of the y-axis. So that means it should be this. It should be this. But there is a catch in the question. That's why this question can damage your score big time. And why it can damage your score is because, read it carefully, they have not asked you root mean square. They have just asked you mean squared velocity. So when I say mean squared, that root is not there. So it is just 3RT by M. It is just 3RT by M. Got it? Yeah, that is the catch. So that's why this question becomes very tricky. And then it is directly proportional to the temperature. So here you can see it is directly proportional to the temperature. So it should be C option. Yes, C option is correct. If root mean square was asked, then what will be the correct answer, guys? If root mean square was asked, then what will be the answer? RMS versus T. Think of this as y-axis, think of this as x-axis. If y is proportional to square of x, then the graph will be a U-shaped parabola. When y square is proportional to x, then the graph is parabola, U-shaped, but it will be sleeping parabola like this. Yes. So then the answer would be B. Then the answer would be B. Got it? So this would be when the RMS speed is asked, not mean square. So here I would use this B option. Got it, everyone? Wasn't this a lovely question? Yeah, be careful. Read the questions carefully. You will feel like, when you're solving the question paper, yes, sir, I solved everything properly. But after coming back, then you realize, oh my God, what mistakes I have made. Anyways, coming to the next question, guys. Before I go to the next section, let me give you one more important kind of question. Let's see whether you guys can solve this. Find the ratio of the RMS to the speed of sound for helium gas. Let's see if you guys can quickly find this out. What is the ratio of the RMS to the speed of sound for helium gas? So we need to know two formulas here. RMS speed formula for any general gas was obviously root 3 RT divided by M. What is the speed of sound in general? Try to recollect sound chapter, waves chapter. It was gamma RT by M. They usually couple these two things, sound and the RMS or average speed many times, and they give you combined questions. Now let's take the ratio and see what exactly do you get. So RMS divided by the speed of sound will be, do you remember this formula? Gamma RT by M. MM cancels, TT cancels, RR cancels. So I'm left with 3 on the top and just gamma over here. Oh, so it's independent. It's independent of the molar mass, and it's also not dependent on the temperature. Both of them just got cancelled. And what is the value of gamma for helium? It is a monoatomic gas because it is an inert gas. for a monoatomic gas, gamma value will be 5 by 3, guys. So this will be 5 by 3. 3 goes on the top of 9. Root of 9 is 3. So 3 by root 5 is the answer. How many of you wrote 3 by root 5? How many of you wrote 3 by root 5? Very good. Yeah. So this is the velocity of the sound. Try to remember those formulas from sound chapter. Velocity of sound in solid is root of gamma, sorry, Young's modulus by density. Velocity of sound in a liquid is nothing but root of bulk modulus by density. Velocity of sound in a gas is also bulk modulus by density. You can write it as gamma p by rho, or you can write it as gamma RT by M. Both are valid. So these were the formulas from the sound chapter. From the sound chapter. I'm just doing a recollection of that. Is that okay? Shall we go ahead? Is that okay, Arjun? I hope you were able to recollect these formulas, or just go back to that chapter, see where it was. But anyways, I have given it over here. Can you make nurture series for 2026? For 2026, we have very big plans, and this will be one of the best things that we'll do for JEE channel in the last 5 years. You guys are going to be very lucky. 2026 and 2027, there is some amazing series which will come up, but it will take some time, guys. Till April attempt, I can't do anything for 2026 much. You need to understand, because the same thing I will do for you when you come to 2026 JEE or 2027 JEE, because right now your seniors need me and my entire team the most. So I hope you understand. Meanwhile, please watch the old classes. Obviously, something amazing is coming for all of you. Okay, let's go to the energy related concepts. I just showed you that every molecule will possess energy. They have different speeds, so different energies, and they keep on exchanging their energies. But as a whole, the energy of the gas remains constant for a given temperature. If you cool it, then the speeds reduce, the energies also will go down. But if you heat it, then the molecules collide with higher speeds more frequently, and then you can see the total energy of the system also keeps increasing. It's not just that the energy of the gas depends on the temperature alone, but it also depends on the nature of the molecules, meaning the degrees of freedom, meaning how many free movements are possible for any kind of molecule. That is called as the degrees of freedom. So I can go up, I can go down, I can go up front, back, left, right. So those are your degrees of freedom. Okay. All right, Sky Mature. I'm so glad. Yes, by April is the time where you can start expecting everything for 2026. Okay, so one of the first important thing which you should know is that there is something called as the law of equipartition of energy. Yes, law of equipartition of energy, which says that, says that the average energy of a molecule or in a gas with each degree of freedom, is half kT, where k is the Boltzmann constant and the value of k is given by R, gas constant, by Avogadro number, which is roughly 1.38 into 10 to the power negative 23. That is your k. T is your temperature. For every degree of freedom of a molecule, not gas, of a molecule, you take a molecule of oxygen. That oxygen molecule can go up, down. That's 1 degree of freedom. Can go left, right. Can probably even rotate. So every degree will have half kT. That's a very teeny bit of energy, because this value, you can see, it's negative power 23, and it is dependent on the absolute temperature also. The moment you increase the temperature, the energy for that degree of freedom will automatically increase. Now, a gas molecule can possess many degrees of freedom. Let's say it has 6 degrees of freedom. Chumma an example. So the total energy of that molecule will be 6 times of half kT, because each degree will have half kT, half kT, half kT, half kT, half kT, 6 times. If a molecule has 29 degrees of freedom, chumma some random example again. So 29 times half kT will be the energy of that particular molecule. Got it? Now, every molecule can possess three types of degrees of freedom. One is translational, one is rotational, and the third one is vibrational. So translation can occur in three directions, one in X direction, one in Y direction, and one in Z direction. So at max, you can have three translational degrees of freedom. Rotation, half I omega square, half moment of inertia into angular speed square. That is your rotational energy. So it can rotate in X axis, it can rotate in Y axis, it can also rotate in the Z axis. So three rotational degrees of freedom maximum. And lastly, the vibrational degree of freedom, when the molecules are not having a fixed bond length, they can vibrate. So they can also have vibrational degree of freedom like SHM oscillations. Is this absolutely clear, everyone? So how many molecules have which kind of degrees of freedom? Quickly, let's make a chart of it. Okay, observe this. Monoatomic molecule, I'll put it over here. Diatomic molecule, or linear polyatomic molecules. We'll put it together. And then non-linear polyatomic molecules. What do I mean by these things? For example, when I say monoatomic, it means just one single molecule, just one single, atom. And diatomic, obviously two atoms with a bond in between. Linear polyatomic means you have three atoms or four atoms or five atoms, but all of them are on the same line. Non-linear polyatomic means something like this, or maybe something like this. All these are non-linear polyatomic molecules. So when you talk about the examples perspective, let me just make some partitions over here. Just 1 second. So examples: monoatomic, helium, argon, neon, etc. Diatomic, hydrogen gas, nitrogen gas, oxygen gas. This can be also even CO2, carbon dioxide, linear molecule it is. Non-linear like CH4, H2O. All these are like non-linear molecules. Okay, NH3. Okay, everybody might have studied this in chemistry. Okay, then these were the examples. These were some of the examples. So these are some of the examples. How about the degrees of freedom? Let's put it over here. Degree of freedom. Usually the symbol for that is F. Monoatomic molecule can move like this, can move like this, can move like this. It does not have rotational degree. So it has three translational degrees of freedom. For a diatomic molecule, it can go up, go front, back, go left, right. And this can also rotate, about this axis. Okay, it can, 1 second. It can rotate about particularly this axis. It can also rotate about this axis, both these molecules. So it has three translational plus two rotational degrees. Totally, it has 5 degrees of freedom. There is a special case in that where when you have very high temperature, then these molecules begin to vibrate. There is some vibration which occurs. And for very high temperatures, only for high temperatures, there is an additional plus two vibrational degrees of freedom, which makes the total as 7. This is only for high temperatures. Every vibrational degree of freedom contributes to two terms of, or 2 degrees of freedom. Please remember that. So when they give you, there is one vibrational degree of freedom, you add it as 2 degrees of freedom basically. Yeah, I hope this is absolutely clear. Then the next thing, or basically if there is mentioning of non-rigid molecule or high temperatures, that's what you should understand. High temperature or non-rigid molecules or non-rigid molecules. For non-linear polyatomic, obviously it can go front, back, left, right like this. It can also now rotate about the y-axis. It can also rotate about the x-axis. It can also rotate about the z-axis. So it has 3 translational plus 3 rotational, and vibration we do not discuss in JEE, but for JEE physics perspective, you should just remember for polyatomic, it has total of 6 degrees of freedom. It has total of 6 degrees of freedom. There is also CP and CV, which you should be aware of. Yes, the terms CP and CV, guys. The terms CP and CV, let's have a look at it quickly. The specific heat capacity at constant pressure, the specific heat capacity at constant volume. Yep, both these terms. So let's start with CV first. First, let's start with CV. CV, the formula is degrees of freedom into gas constant divided by 2. So if you see F is 3, so this will just become 3 times R by 2. Here, it will just become 5 times R by 2. Here, it will become 6 times R by 2, which is basically 3 times of R. Only for this very special case where high temperature is there, then 7 degrees of freedom will come. So it will become 7R by 2. But this is only for that special case. Otherwise, this will not be true. Is that okay? I hope this is absolutely clear, my dear students. This is only for that high temperature or non-rigid case. Let's go to CP now. CP is nothing but CV plus R. What is this? This is called as Mayer relation. Mayer's relationship. Mayer's relationship. CP is more than CV by R. So if you add R to it, you will get 5R by 2. If you add R to it, you will get 7R by 2. If you add R to it, you will get 9R by 2. If you add R to it, you will get 4R. So this is another thing which you should obviously know. The last thing over here is gamma, which you can write it as CP by CV, which is also 1 plus 2 by degrees of freedom, which is also 1 plus 2 by degrees of freedom. If you put the degrees of freedom as 3, 2 by 3 plus 1, 3 plus 2 is 5, so 5 by 3, yes. Or divide this with this, R, 2 cancels, so this will also become still 5 by 3. So either use this by this or 1 plus 2 by F. F is the degrees of freedom. Here, it will be 7 by 5, of course. This will be 7 by 5. In an extreme case, just like for higher temperature, 9 by 7 will be the answer, not every time. And this one will be obviously 4 divided by 3. This will be obviously 4 divided by 3. Is that okay, guys? Everybody? Yep. Okay. Okay. Mass of a molecule is molar mass by number of molecules. Mass of a molecule. Okay. Brilliant brushes. Okay. Let's do some questions based on that also now. So, in this particular slide, when I said half kT is the energy per degree of freedom. So, energy of a molecule will be degrees of freedom into half kT. But if you take the total energy of a gas, when you will have to multiply N with the energy of each molecule, each molecule will have some energy, N molecules are there, that will give you the total energy of the gas. So that answer comes out as moles into specific heat capacity at volume and into temperature. So this is the formula which you get for a complete gas. This is the formula which you get for a molecule. They are two different things. NCVT is for a gas, half kT into F is for a molecule. Okay, so this is going to give you the energy of a gas. So this is nothing but the internal energy of a gas. And in according to KTG, this is only going to be kinetic energy only. Potential energy will be zero. And the reason for this to be zero is because since interaction is neglected, or the forces, intermolecular forces are negligible. So that's why the potential energy will be zero. All the energy of the gas will be purely in the form of kinetic energy. Keep these things in mind. So let's solve the questions, guys. Energy of 10 non-rigid diatomic molecules at temperature T will be. Come on, think carefully and answer this particular question, guys. Of 10 non-rigid diatomic molecules. So the moment you hear the word dia, think of 3 translation, 2 rotation, and 2 vibrational degrees of freedom. So totally, if you add them, 3 plus 2 plus 2, that is basically 7 degrees of freedom. 7 degrees of freedom. Correct? Now, what is the energy of a molecule? I just told you it is degrees of freedom into half kT. So degrees of freedom is 7. So 7 into half kT is the energy of a molecule. So obviously the question is something else. So for 10 non-rigid molecules, the energy is the energy is how much? The energy is how much? That energy will be 10 times of whatever this number is. 7 multiplied by half kT. 7 multiplied by half kT. That's it. So that's it, guys. 10 by 2. 10 by 2 is 5. So 7 5s are 35 into kT. 35 kT is a D option. Perfectly correct. D option. Everyone, how 7? 3 plus 2 plus 2. That is why it is 7. 3 degrees of translation, 2 degrees of rotation. Non-rigid means the molecules can change their bond length. That means they can vibrate. So whenever vibration is considered, it is considered as 2 terms. So 2 degrees of freedom will come, which will give you 7. Is that okay now? Great. Yes, D is the answer. Yes, I am sure. Very good. Everybody, shall we go ahead to the next question quickly? Give me a thumbs up. And if you have forgotten to smash that like button, please do that right now. Every day, your captain, your team is coming over here. That much amount of sincerity, that much amount of feedback is mandatory, guys. We are doing this for you. So make sure you're marking your attendance, subscribing to the channel, putting up the comments. Yes, sir. This particular lecture done, this day done, NTA revenge day 3 done, waiting for the next class. I want these comments, guys, after the session is over. Okay. Moving on to the next question. So Praveen, basically, see, I just told you, right, over here only. Where did it go? Half kT is what? The energy of a molecule per degree of freedom. Half kT is the energy per degree of freedom for a molecule. If there are 5 degrees, you multiply it 5 times. If there are 6 degrees, multiply it 6 times. If there are 7 degrees, multiply it 7 times. Okay. This is the formula for the total gas. All the molecules energy, you add them, you will get the total gas energy. Now, I just showed you over here, when you have a diatomic molecule like hydrogen, nitrogen, etc. Yeah, hydrogen, nitrogen, okay, etc. 3 translational degrees are there, 2 rotational are there. When you go for non-rigid, you add 2 extra vibrational degrees, which will make it 7. Remember this? Okay. So now come back to this question. So for a molecule, how many degrees of freedom are there? 7. So 7, if you multiply by half kT, you will get 7 by 2 kT. Cool. But that is for a molecule. How many such molecules are there? 10. So multiply this by 10. So 10 and 2 cancels, becomes 5. 7 5s are 35. So it's 35 kT. Is that okay? Understood now? All right. Moving on to the next question. The energy of translation of the molecules in 50 grams of carbon dioxide gas at 17 degree Celsius. Read the question again so that you understand it properly. Only they have asked for translation for the molecules in 50 grams of carbon dioxide. Okay. Now, tell me what is the molar mass of CO2, guys? Molar mass of CO2. Oxygen is 32. Yes. Come on. Yeah. Carbon dioxide. Everyone. How many moles will be there? From that we'll get. Yep. Everyone. Come on. Very good. Who is that? Juko, Jalwan. Awesome. So it is 44 grams. So can you tell me how many moles are there in this? How many moles will be there? Moles of CO2. It will be 44 divided by 50 over here. 44 divided by 50. Very good. Oh, sorry. My bad. I did it exactly opposite. 50 divided by 44. That many moles are there. Very good. But they have asked the total kinetic energy of the translation for these many moles. 17 degrees Celsius also I do not like. Convert it into Kelvin. Add 273 to it. Add 273 to it. It will become 290 Kelvin. Yes, it will become 290 Kelvin. Whenever you have to find the energy of a gas, the formula which I recommended was the energy of a gas is number of moles CV into T. Number of moles into CV into T. Remember it? NCVT. But this will give me the total energy of the gas, which I don't want because that also accounts for the rotational degrees of freedom. Here only translation is asked, so I need to be little bit careful. Little bit I need to be careful. So the total energy of translation will be for that entire gas. Observe carefully. Every molecule will have 3 degrees of translation. Each translational degree will have half kT worth of energy. So this much is just the translational energy per molecule. Translational energy per molecule. If I multiply this with number of molecules, won't I get the total amount of energy? If I multiply this with the total number of molecules, won't I get the total energy, guys? Everybody with me? So what is the total number of molecules going to be? It's going to be, this is going to be number of moles multiplied by the Avogadro number. Number of moles multiplied by the Avogadro number. Moles, I just got it from here. How much is the moles? It is nothing but 50 divided by 44. Avogadro number 6 into 10 to the power 23. So this much part is done. This much, the first part is done. Now what about this? This is nothing but 3 multiplied by half multiplied by 1.38 10 to the power negative 23 multiplied by the temperature. What is the temperature? That is 290. That is nothing but 290. Now just do the math and see what is the answer that you are getting approximately. 10 to the power positive 23 minus 23 will get cancelled, guys. Yep, you can see that. Many things will get obviously cancelled here. This and this will get cancelled. This 2 will get cancelled with this will become 3. 3 3s are 9. It will become 50 by 44 also. You can write it as 22 over here. This is 25 over here. Correct? So many things you can simplify and see what is the answer that you guys are getting. Yep. Is it close to 4,200, 3,600, 3,900, 4,100, guys? Come on. Quickly see what is it coming out approximately as. What is it approximately coming out as? Which of these options is it coming out close to? Yep. Is it one of this or this. I think it is D. Just check it out. If it is coming out close to option D, around that much, 4102, around 4102, guys, 4102. Just check it out. 290, close to 300, 300, and this 3 will make it 900. 900 into 3 will make it 2700. Then you have 1.4 times over there and 25 also. So come on, guys, you should be able to get it. And then you have to see this also. Just check it out. Almost close to 4102. Very good. Awesome. Yes, very good. So I hope you understood how to solve this kind of questions. These kind of challenging questions can come in your JEE examination April attempt. Okay. Let's go to the next question, guys. I want you to get used to all the models of the questions. If the temperature of the gas is this much and the average energy of the translation is K, the temperature at which the translational energy of the molecules of the same gas becomes double. Now, guys, see very simply, the translational kinetic energy of translation of the molecules will be, there are 3 translational degrees of freedom. Each degree of freedom is half kT. There will be n number of molecules, so it will be n into 3 into half kT. 3 because there are 3 translational degree of freedom, and this half kT is because of law of equipartition. Law of equipartition of energy. N is the number of molecules. N is the number of molecules. As you can see, the energy of the translation is directly proportional to the temperature. So kinetic energy of translation is directly proportional to the temperature. So if you want to double this, even the temperature should be doubled. So initially the temperature was minus 78 degrees Celsius. So first of all, convert minus 78 into Kelvin, guys. How much is minus 78? Yep. How much is minus 78 in Kelvin? Yep. How much is minus 78 in Kelvin? Add 273 to it. Add 273 to it. See how much will it be? 195 Kelvin. 195 Kelvin. Okay. So the new temperature. So the new temperature. The new temperature will be 195 multiplied by 2, which is just going to be very good, 390 Kelvin. Excellent. But none of the options are in Kelvin. No issues. Subtract 273 from it so that you get it in degrees Celsius. So that you basically get it in, yep, degrees Celsius. See what the units are. If you miss the units, then again you will get a wrong answer. Correct. So how much will it be? 117 degrees Celsius, which is D option. Perfect. D option is there over here. Okay. So again, the use of law of equipartition of energy related concept and formulas. Usually these questions are always tricky. Cool. Let's go to some thermodynamics questions. Let's go to some thermodynamics questions. Very good. Okay. Now in thermodynamics, there are 3 terms which you should know. One is heat, one is internal energy, one is work. This is the main law of thermodynamics which is there throughout the chapter. So it says that if you give heat to the gas, then that heat will get absorbed. It will change its energy of the gas, meaning the internal energy. And the gas might also expand in that process. So it will end up doing some work. So this is the formula that you should definitely remember. Whatever heat is given to the gas, there will be some change in the internal energy, and obviously there will be some work done. There will be some work done by the gas. Now, how do you calculate each one of them? Let me go through that. First of all, whenever you want to calculate heat, keep this in mind. Whenever heat calculations are there, keep this in mind. Your heat calculations will be either M C delta T, or it will be N C delta T. Usually here we also use the symbol S instead of C. This M is mass. This is specific heat capacity. Delta T is change in temperature. This N is the number of moles. This is molar specific heat capacity. Molar specific, molar specific heat capacity. This formula generally use it for gases. This formula you generally use it for your solids and for liquids. Generally for solids and for liquids. So there you don't talk in moles. So MS delta T is for solids and liquids, where this is just specific heat. This is molar specific heat capacity, which is NC delta T. Now, what is very important that you should know is that this particular C, molar specific heat capacity, completely depends on the process. It depends on the process that is being undertaken. For example, if it is isobaric, it will be Cp. If it is isochoric, it will be Cv. If it is isothermal, it will be Ct. If it is adiabatic, it will be Ca. This value of Cp and Cv, we already know. It is R upon gamma minus 1, or it is degrees of freedom into R by 2. Either of these two formulas you can use, where gamma is your Cp by Cv ratio. This Cp also can be written down as gamma R upon gamma minus 1, or you can also write it as Cv plus R, which is your Mayer's relationship. Cv plus R. If you know Cv, just add R to it. You will get the value of Cp. Yep, everybody remembers this Cp, Cv values. We just did it just before doing these questions over here. Yeah, the Cp and Cv values, Fr by 2, Cv plus R, all these things. Now, what is this Ct and Ca? Ct, specific heat capacity at constant temperature. Well, think about it, my dear students. If I write Q is equal to Nc delta T, for isothermal process, delta T will be 0. So, if you take this 0 below, if you bring this over here, any number by 0 or close to 0 will make that very, very large. Denominator is very small. It will become very large. So, C for that process will become infinity. Yes, C for that process will become infinity. So, Ct tends towards infinity. Ct tends towards infinity for isothermal process. Ca, adiabatic process. Q itself is 0. So if the LHS is 0, RHS, at least one term should be 0, so that their product is 0. Delta T N can't be 0. So it is the specific heat capacity which is 0. So for adiabatic process, Ca is 0. Adiabatic process, Ca is 0. Is that okay? Is that clear, everyone? Great, great, awesome. This heat part, everyone clear? Last thing, sign convention. Whenever heat is positive, that means heat is absorbed, absorbed by the system. That is, by that gas, it has absorbed. And by chance, if the heat is negative, then it has been released, released by that particular system. If you heat it, it is positive. If you cool it, you are taking away heat from the system, then it is negative. Keep this in mind. Next important thing, my dear students, delta U, internal energy. Internal energy change. Please remember, this is completely a state function. It is a state function. So say for example, there are two different processes. There are two different processes. One goes like this and you reach here. The other goes like this, like this, like this, and you reach over here. This is the first, this is the second, this is A, this is B. Now, the change in internal energy between 2 and 1, or from 1 to 2, is the same whether you go via A or B. Same for A and B. It is a completely state function. Please mind it. Okay. Only when you take an ideal gas, the change in internal energy of an ideal gas, remember U was NCVT, so delta U will be NCV delta T. It will be NCV delta T. Change in internal energy of a gas for any process. Please mind it, for any process. For any process, it is always going to be the same. All the processes. All the processes. Where we use Cp and Cv, if the process is mentioned to be isobaric or isochoric, that's where you will use Cp and Cv, obviously. Or wherever it is asked, like what is the Cp of the gas or what is the Cv of the gas. Whenever you have to find internal energy of the gases, like you have seen over here, uh, whenever you have to find internal energy of the gases, you will always use Cv. It is never ever Cp. Whatever the process is, always you are going to use Cv for finding the internal energy calculations. Last thing is the work done calculation. The work done is given by integral of PdV. Work done is always integral of P pressure into volume. It's also the area under the graph. Yes, it is nothing but your under pressure versus volume graph, and always it is work done by that particular gas. Always remember this, work done by the gas. So whenever it is positive, please remember it is by the gas. That means most likely the gas has expanded. Then whenever the work done is negative, it is work done on the gas. That means it has contracted. It has compressed. So if it is positive work done, you will see the volume will increase. If it is negative work done, you will see the graph will have an arrow mark going backwards. So that is the difference between positive work and negative work. Okay, between positive work and negative work. Also, this work done process, this work done calculation, this work done is not a state function, it is a path function. It is a path function, which means it depends on the process. If the process is different, the work done is also going to be different. Is that clear? Yeah. Okay, great. Very good. Excellent. Great. Now, let's go to the cyclic process and then we'll see the different processes. Do you want me to give a chart and a table which will help you remember all the things? Yes or no? Let me see. Come on, guys, put up some fire. And if you have forgotten to smash that like button, let me see whether the likes increase. Yeah, quickly. Do you want me to do that? Smash that like button right now. Yes? Okay. Listener, I'm just going to do that. Whatever you said, see, I'll listen to you. Okay, great. Okay, Javan, I will just probably give a brief about it. No issues. Okay. Observe this carefully. Observe. I'm teaching now properly. See, cyclic process. Cyclic process means you have come back to the same state. You have come back to the same state after a series of some methods or processes. You do something, expand, contract, expand, 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 contract, contract, heat, cool, whatever. You are back to the same initial conditions. So in always such a process, because you are coming back to the same situation, can you quickly tell me what will be the change of the internal energy? Delta U, I just told you. What is delta U, guys? It is a state function. So if you are coming back, molar same Cv is constant and delta T, you are back to the same thing. It will be 0. So yes, always for any kind of cyclic process, delta U is 0. Delta U is 0. Now we all know that the heat is delta U plus work as per the first law of thermodynamics. Since delta U is 0, what can you say? All the heat is going to be the work. All the heat is going to be the work. So whatever work you calculate, exactly same total heat will be involved. Cool. Q is equal to work done. That is also another important thing. Third important thing, How do you calculate heat or work? Calculations of work are usually easier. So the work done basically becomes the area enclosed within that cycle. Yes, this area enclosed inside that cycle gives me the total work per cycle, work per cycle of the gas, how much work it has done per cycle. If you keep on repeating that cycle, obviously more number of times that work will be done, but per cycle, how much work has been done. Please remember, if it is clockwise, then it is positive. This is clockwise, assuming the graph is pressure volume. And the same thing will be negative if it is anti-clockwise. If it is anti-clockwise, then it is negative. All this is assuming it is a pressure versus volume graph. It is a pressure versus volume. If it is volume versus pressure, this is exactly opposite, obviously. Okay, so if it was volume versus pressure, then clockwise will be negative, anti-clockwise will be positive. So sometimes positive work is done, meaning the work is done by the gas. That means it has expanded. Negative work is done. That means it has contracted. Okay, so then it will be negative. The work will be done on the gas. Is that okay? Everybody with me? All these things related to the cyclic process. Now, there comes a very interesting thing over here. Observe this carefully. Observe this carefully. Imagine there is some kind of cyclic process like this, and in some parts you are absorbing the heat, some parts you are releasing the heat, some parts you are doing work, some parts you are getting the work done on you, etc. So if there is a cyclic process, and observe this carefully, there is some heat which you are absorbing, there is some heat which you are releasing. So if you see, the total heat will be Q, which you are absorbing, minus the Q which you are releasing. Similarly, this total heat, if you count it properly, this will be also equal to the total work done, in the cycle. And all of this is because delta U will be 0 in that particular cycle. We just saw total work and total heat will always be the same thing. Total work and total heat will always be the same thing because delta U is 0. Then, whenever the graph, keep that in mind, whenever that particular graph happens to be in the clockwise direction, then you can consider it like a heat engine, a heat engine, a heat engine, meaning what it is doing is, because it is clockwise, the work done, this value will be positive. That means it is doing work because of some thermodynamic processes happening in it. Some heat, cool, something is happening because of which it is ending up doing net work. And that is exactly what the engine of a car or a bike does. You put some fuel, you burn it, there is some combustion, the gases expand, they move the pistons inside the cylinder, which in turn rotate the shaft and turn your wheels, and you draw mechanical energy. So the job of an engine is to utilize the energies of those fuels, burn it, basically absorb the energy, absorb the heat, and then convert it into a mechanical form of energy. So heat engine, what it does is basically it absorbs 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 heat, and eventually it ends up doing work. Is this absolutely clear, my dear warriors? Is this absolutely clear? So if it's a good engine, what should it do? It should do a lot of work with very little fuel. That means it should absorb very little heat and it should do a lot of work. So you derive, or you basically call the efficiency of an engine. This is nothing but the efficiency efficiency of an engine. Efficiency of that engine is nothing but how much work you are doing per cycle upon only how much heat you are absorbing. If you multiply it by 100, you will get it in percentage. If you leave it, it will be in fraction. Let's say, for example, in that entire cycle, you did 70 joules of work. The heat which is absorbed was, let's say, I don't know, I'm saying something like 100. The heat which was released was 20, or basically 30, my bad, because 100 minus 30 will be 70. So if I ask you the efficiency, what will you write? Work done for that cycle is 70, absorbed is 100, multiplied by 100. So it will be 70% efficient. It will be 70% efficient. Is that clear, everyone? Everybody give me a thumbs up if you understood what efficiency, what heat engine exactly is. Let me know, guys, quickly in the chat box right away, right now. Now, the best efficiency comes for a Carnot engine. So this is any engine. This is any engine you can use this formula for. The best efficiency is for Carnot engine. This is the highest efficiency which is possible, which is won by the cold temperature by the hot temperature. This is the max efficiency, maximum possible efficiency that you can get for a Carnot engine. That TC stands for the cold temperature, the cold or the low or the sink temperature, the sink temperature. TH stands for the hot or the high or the source temperature or the source temperature. This is not there in the syllabus, but just I'm giving it to you in case you need it for any other local entrance test or maybe for your private entrance examination. Okay, is this clear? Absolutely. Okay. Now coming back to the different processes, guys. So quickly, let's talk about isochoric process. Then we have isobaric process. Then we have isothermal process. Then we have adiabatic process. And lastly, polytropic process. All these are different processes. Let's see the different terminologies associated with them quickly. Hmm. Starting off with, in isochoric, what is constant? Volume is constant. So that's why pressure is directly proportional to temperature. Isobaric, pressure is constant. So volume is directly proportional to temperature. Isothermal, temperature is going to be constant. So your pressure into volume is constant, or rather pressure will be inversely proportional to the volume. Okay, correct? Okay. Adiabatic, your pressure into volume raised to gamma is constant, or temperature into volume raised to gamma minus 1 is also constant. Okay, that is what happens in adiabatic. In polytropic, just forget the gamma, replace it with any number. Let's say I call it x. So PV raised to x, x is any real number that is constant. In fact, adiabatic is a special case of polytropic where x is gamma. If x is 1, then PV will be constant. It will become isothermal process. If x is basically 0, V raised to 0 is 1. So P into 1 is P. So P will be constant. So it will become isobaric process. So actually all these processes are special cases where x are different values. So I can just mention what the value of x will be. Here the special case will be where x is gamma. Here the special case will be x is 1. Here the special case will be x is 0. Here the speciality will be x is infinity. So when you put different values of x, you get either adiabatic, isothermal, isobaric or isochoric processes. Is that clear? Yep, definitely. Okay. Very nice. Very nice. Now, the next important thing, my dear warriors, the next important thing, observe carefully. Once this is done, we will talk about delta U everything. So, internal energy change always is going to be NCV delta T. NCV delta T. NCV delta T. Even if it is isobaric or isochoric, doesn't matter. For isothermal, delta T is 0, so it is 0. This is only because delta T is 0. So when you multiply 0 with anything, it will be 0. Okay, so that is the reason for it. Okay, then in adiabatic, again it is NCV delta T. In polytropic also NCV delta T. For all processes, keep this in mind, delta U is NCV delta T only. Next thing, your heat and work. Let's come to that. Let's start with work now. Work. Work is, remember, integral PdV. Work is, remember, integration of PdV. Okay. For isochoric, there is no change in volume, neither increase nor decrease. When it increases, it is positive. When it decreases, it is negative. When there is no change, volume is constant, it will be 0. Isobaric, because pressure is constant, integration of dV will become delta V. So it will just become P delta V, which is the same as P into V2 minus V1, which is also the same as NR delta T, which is also the same as NR delta T. Either this or this, anything will do. Isothermal process, the formula is nRT into log of V2 by V1, which is also the same as nRT log of P1 by P2. Obviously, PV is constant, so V1 by V2 will be P2 by V1. So this is either one of them you can use. Adiabatic process, guys. What's the formula for that? Yep. Come on, guys. It is nothing but NR T2 minus T1 upon 1 minus gamma. NR T2 minus T1 upon 1 minus gamma. Keep this in mind. Okay. Lastly, over here, for polytropic process, it is exactly similar. Instead of gamma, you put that number x over here. That's it. So it will be NR final minus initial temperature whole thing upon 1 minus x. That's the only change. That's the only change. Okay. Finally, let's come to heat. Let's come to heat. Remember, heat is your whatever delta U you got over here, delta U you got plus that work done, plus that work done. So this plus this should be the answer. So anyways, here it is isochoric. So it should have been NC for that process into delta T. Remember, for heat, the formula for C will keep changing. Cp, Cv, Ct, Ca. It will keep changing. So keep that in mind. For isobaric, instead of Cv, it will be Cp. So it will be NCp delta T. For isothermal, well, I know that the total heat will be this plus this. This is 0. So the total heat will be just that work done, which itself is nothing but nRT log V2 by V. So this will be this plus this. So this plus this means 0 plus this number. So as it is. For adiabatic, it is 0. Yes, the adiabatic, the value is 0. No heat will be absorbed or released. For polytropic, it will be just NC for that particular process into delta T. This can be calculated using this and this. So it can be anything. It can be just anything. Yeah. Formula for CT, I just gave it to you right over here. Where did I go? CT is infinity. CT is infinity. CA is 0. CA is 0. CT is infinity. Okay? Cool, guys. All formulas discussed. Can we go with the questions now? All formulas almost discussed. Yes, let's go with the questions. But one more thing I will just give you before we go to the questions. This is also quite useful in some of the things. Whenever you have pressure volume graph and that graph is some curved line, then That will give you a tangent, that is basically a slope. Okay, so this is a tangent to that particular graph, and that graph is, let's say, P into V raised to X is some constant. This is any process, isothermal, adiabatic, doesn't matter. X is some real number. It's a polytropic process. So keep this in mind. The slope, which is dP by dV, which is nothing but the slope of pressure versus volume graph. The slope of your pressure versus volume graph. This dP by dV is going to be always, keep this in mind, negative X pressure at that point by volume at that point. Very important. At that particular point, you find the pressure as well as the volume and divide them and put a negative sign. Along with that power which volume is raised to, you will get the slope of that. This is again very important, guys. So from this, we can take some example. Say for example, for isothermal process, since P into V raised to 1 is a constant, so this 1 becomes your X. For adiabatic process, PV raised to gamma becomes constant. So this gamma becomes your X. So for isothermal, X will be 1. For adiabatic, X will be gamma. So can you not see now the slope of adiabatic? The slope of adiabatic will be minus gamma times P by V, and the slope of isothermal graph will be just minus P by V, because that X value will be 1. So adiabatic has more steeper slope as compared to isothermal graph, gamma times more. Okay. Is that absolutely clear? Cool. Let's do some questions, guys, coming up on your screen. But remember, we had left few questions somewhere. So we'll just go to those star mark questions and then go ahead. Okay. With the increase in the pressure of the ideal gas, come on, try to solve this. The volume falls off more rapidly in isothermal in comparison to adiabatic. In isothermal, PV is constant, whereas adiabatic PV raised to gamma is constant. Here, gamma is the ratio of specific heat, P is pressure, V is volume. What do you think about it? Good afternoon, Shankar, Gayatri. Welcome, everyone. For isobaric, dq plus work is equal to... No, Mahalakshmi, you are getting confused between chemistry class and physics class. In our physics class, remember, heat is delta U plus work. In chemistry, it is different, so don't get confused. Yeah. With the increase in the pressure, come on, guys, the answer is both are true, and it is also the correct explanation. What is the reason for it? I just told you about, these graphs, right, just now. If this is pressure, this is volume. For adiabatic, the slope is higher. This is adiabatic graph. If you compare it with isothermal graph, it will be like this. This will be your isothermal graph. So, with the change in the pressure, with the increase in the pressure of an ideal gas, the volume, will change more rapidly for isothermal graph as compared to, this thing. So, I don't think we should decrease the pressure. We should have increased the pressure. So, let me go like this. This is better. So, this is your isothermal graph, and we are trying to increase the pressure. Here also we are trying to increase the pressure. So when I increase the pressure, as you can see, the volume falls more rapidly for for an isothermal process as compared to the adiabatic process. So for that, what you do, draw a horizontal line to do the comparison. Draw a horizontal simple line and you will get the answer. See, when I go from this pressure to this pressure, I have increased the pressure by this much amount, delta P. Can you see my adiabatic process, the volume changed by this much. So this was the volume change in adiabatic. Whereas if you compare it with isothermal, see the volume has come till here. So the volume has changed by this much. This was the change in volume for isothermal process. Isothermal process. So obviously the volume falls more rapidly for isothermal process as compared to adiabatic process. And what is the reason for that? Because the manner in which the pressure and volume are related to each other. For isothermal process, it is P into V, which is constant. For for adiabatic process, it is PV raised to gamma, which is a constant. So that power to which volume has been raised to makes that whole difference in that curvature, because of which the changes in the volume are different. Is that absolutely clear? Everyone, give me a thumbs up quickly. Very good. Excellent. Great. Let's go then to the next question, guys. Coming up on your screen. Where did it go? Yeah, this. The work done in adiabatic changes in an ideal gas depends on. The work done in an adiabatic process for an ideal gas depends upon what exactly? Everybody spam the answer quickly. What is the correct answer? Work done, adiabatic process. Try to recollect the formula. The work done for adiabatic process is Nr T2 minus T1 upon 1 minus gamma. So pressure, temperature, heat capacity, volume. None of them are there except for temperature, guys, over here. So I think it should be C for Captain Shreyas. Sorry, B for Bombay, my bad. Yeah, changes in the temperature. Yes, perfect. Very good, Arjun, Ivan, Abhirami, Jarvis. Proud of all of you guys. Very good. Let's move to the next question on your screen. The magnitude of how much heat is exchanged by the system is given in a cyclic process as how much? Everything is in SI units. Check this out. Volume is in no, they have asked in SI units, my bad. They have asked in the SI units. They have not given necessarily in the SI units. Pressure over here is in kilopascal, volume is in cc. So the question is, what is the heat exchange? Now we know that for a cyclic process, because delta U is 0, that particular heat will be the work which itself is the area which is enclosed. In this case, the area of the circle, which is the area of the circle, which is pi multiplied by the radius square. So what is the radius? Well, is it a circle first of all? Yes, because the diameter vertically is 200 units. The diameter horizontally is also 200 units. 100% it's a circle, else it could have been an ellipse also. So what might be the radius? Obviously the radius will be diameter's half, so it will be 100 units. It will be 100 units. So the radius, I will have to put it as 100, okay, square. But be careful with the units. This is kilo. So the vertical axis unit will be kilopascal multiplied by the horizontal units will be cc. Cc. We'll take care of it in the next step. For now, it is 100 square. 100 square, which is 10 raised to 4 into pi. Kilo is 10 to the power 3. Pascal, I will keep it as it is. Centimeter is 10 to the power minus 2 meters. 10 to the power minus 2 meters and the cube of it. And the cube of it. So this will be 10 to the power 4 pi, 10 to the power 3. This will be 10 to the power minus 6. This will be Pascal into meter cube. Perfect. So 3 and minus 6 will become minus 3. Minus 3 and plus 4 will become just 1. So 10 pi Pascal meter cube. What is this Pascal meter cube? It is nothing but joules. So 10 pi joules will be the answer. Sorry, the answer given here is wrong. It is 10 pi joules. Yep, 10 pi joules. No, it is not C. It is 10 pi joules, guys. This is the correct answer. Is this absolutely clear? Okay. Awesome. 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 Let's go to the next question on your screen. Hmm. What is it? Choose the correct answer from the options below. Okay. This one is clear, guys. Why we have taken circle? Because the diameters are same. Okay. The diameters are same. That's the reason for that. Okay. But A, B, C, A. Oh, guys, there is one catch over here. My bad. Maybe I think the answer is also 5 joules. This was for the entire circle. So sorry, this was for the entire circle. But in this case, the process that they have asked is A, B, C, A, which is exactly only this much, which is exactly this much. So if the real question was, if the real question was actually what is the heat in only A, B, C, A, then it will be half of the heat for that entire cycle. So therefore, technically this is half of 10 pi, which is exactly 5 pi. Because they have not asked for the entire ABCD cycle, they have only asked for this much part. So it will be half of it. So it will be semicircles area. So this answer will be therefore correct. Yes, this answer will be correct. Yep. Is that okay? Yeah. If it was for the entire A, I did not read this C alphabet here. I thought it was A, B, C, D, but actually they have given A, B, C, A. So if it is A, B, C, A, obviously it is semicircle, then you have to take it as half. So then undoubtedly the answer will be 5 pi, else the answer would have been 10 pi joules. Okay, next question, match the following. Choose the correct options over here. Who will match with what? Come on, this is very straightforward and this has come even in 2024 many times in many shifts. So let's see how you can do this. Yep. Option A will go with what? Pressure varies inversely with volume of an ideal gas. Oh, A is going with 3, guys, directly. For isothermal process, pressure is inversely proportional to volume. A is with 3. You can see over here in C option or in D option. So now check only B option, you are sorted. Or anyone, C option or D option. Heat is neither absorbed or released. Heat is neither absorbed or released. That is obviously adiabatic process where Q is 0. So C goes with 1. So C goes with 1. Obviously this has been eliminated now. So the correct answer will be D. You don't even have to check any other options. Automatically they will match. Obviously B will go with 4. B will go with 4. That means heat absorbed goes partially to change internal energy and work. For isobaric process, exactly that's what happens. Q will go to delta U and work by first law. And for the last option, no work is done. That is isochoric process. That is isochoric process. No work is done because volume will not change. So that is B over here. And this is B over here. Okay, cool. Everyone? Yep. Definitely, Lazia. I will arrange a specific playlist. Very important. I know. I will do that. No issues. Okay. I will get the team to do that. Using the given diagram, the work done by the ideal gas along A, B, C, D. A to B, B to C, C to D is how much? Okay. Come on. Try this out. Oh, it's already arranged. I'm not so sure. If it's not arranged, I will get it done. If it is arranged, then great. So see, my dear students, over here, from A to B, the volume is increasing. So if the volume is increasing, the area should be considered as positive, isn't it? Area should be considered as positive. So height is P naught, width is V naught. So it will be P naught V naught with a positive sign. Why? Because the gas is expanding. So there is expansion over here. Expansion over here. Next, if you talk about B2C, there is no work done. Why? Because the volume is constant, so ignore it. From C to D, just take this complete volume, guys. This area, complete area. So how much will this particular area be? It will be negative because it is compression. Height is 2 P naught. Width is V naught to 3 V naught. Again 2 V naught. So it will be minus 4 P naught V naught. Okay. Here this part B to C, no work done. This is isochoric. Isochoric, always zero work will be done. So therefore, the total work done will be negative 4 P naught V naught plus P naught V naught, which is minus 3 P naught V naught. So option B is the right answer. Option B is the right answer. Minus 4 plus 1 is minus 3. Yeah. Oh, this was your shift question. Wow, very good. Great. Great. All right. Next question on your screen now. If there is an ideal gas which goes from initial to final state during the process, the pressure of the gas increases linearly with temperature, clearly mentioned. The pressure of the gas changes linearly with temperature means P is directly proportional to T. That means V is basically a constant. That means it is a isochoric process. Now try to answer based on that all these questions. Yep. The work done, isochoric process, the work done 100% is zero. This is correct, guys. A statement is correct. Okay. Heat is different from the change of the internal energy. Let's understand this. Because it's isochoric, work done will be zero. So heat will be delta U plus work, which will be zero over here. So all that heat is going in the internal energy. What do you think, guys? No, I don't think that is correct. Heat will not be different. It will be, in fact, the same. So B is wrong. Volume of the gas is not increased. It is actually the same. The internal energy of the gas is increased. Yes, if temperature increases, delta U will increase. So obviously D is correct. Everyone. The process is isochoric, obviously, that is also correct. So A, D, and E, which is B option, yes, it is the correct option. Yep. Oh yes, for UGEE also we'll be doing very soon. For UGEE also we will be doing. Don't worry. Okay, cool. Let's go to the next question on your screen. There is a polyatomic molecule. Obviously, 6 degrees of freedom. So CV will be 3R, CP will be 4R. I had given you the chart. Okay. Pressure A, volume A is given. Pressure B, volume B is also given to point C, point C's pressure and volume are also given. A to B is adiabatic. B to C is isothermal. Okay. This is very interesting. A to B is adiabatic path. A to B is adiabatic path. And then you have B to C, which is isothermal path. Okay, perfect. Question is net heat absorbed per unit mole. That means for a mole, how much heat is absorbed? One thing is very clear. Because A to B is adiabatic, I mean the heat which will be absorbed from A to B will be zero because it is adiabatic and that is the nature of adiabatic process. So the only thing which is remaining is finding B to C. This has now been downgraded to a simpler question. Is that right? This has now been downgraded to a much simpler question. So the question is, what is the heat from B to C now that we have to calculate? How do I calculate heat in adiabatic process? Sorry, isothermal process, my bad. B to C is isothermal. So heat from B to C, which is isothermal. We know in isothermal, delta U is 0. So whatever heat is there, that will also be the work done from B to C. And this is because delta U will be 0 for isothermal process. For isothermal process, how do I calculate the work done? The work done is nRT log of final volume by initial volume. So nRT log of final volume, which is Vc, by initial volume, which is Vb. But I do not know the temperature of that particular gas. I do not know the temperature of that particular gas. Oh, why did they give Already they have given 450 Kelvin. If they are given 450 Kelvin, then my job is done, guys. I don't even have to think about it. Yep. Is that right? Yes, perfect. So just have to put it per mole. So N is 1, R is R. Okay. Temperature is already given to be 450 log of final volume by initial volume. VC. VC is 8. VB is 6. Both are 10 to the power minus 6. So anyways, it will get cancelled. Okay, so this will be 450R log of 8 by 6, which is 4 by 3. Log of 4 by 3. So, which is also by principle of logarithms, 450R into log of 4 minus log of 3. Log of x by y is log x minus log y. So that's it, guys. The total heat from A to B to C, this is 0, this is this. So 0 plus 450 R log of 4 minus log of 3. That's it. So that is your option number B. Very simple. It initially looks like a complex question. Yes, it initially looks like a complex question, but actually it is not. Is that clear, everyone? Okay. Very nice. Very nice. Moving on to the next question, guys, coming up on your screen. Wow, we have a crazy question coming over here. The gas is obeying some weird equation for this particular path from A to B. And the question is, the net work done in that complete cycle is the real gas within a closed chamber at 27 degrees Celsius. That means temperature is constant. And this is the path which it is taking. Question is, what is the net work done? That means you have to basically find that area under the curve. But if this was a triangle, it would have been easier, but it is unfortunately not a triangle. At least by common sense, can you eliminate one option and tell me which is that option which is eliminated, sir? Yes, sir, this option 100% eliminated, sir. This option will not be there, sir. Can you guys quickly tell me which is that option which should be eliminated? Come on, everyone. Yeah, the negative value. So it can't be A. It can't be A. It can't be A. Because can you see it is clockwise? If it is clockwise, it has to be positive. Very good. So if you had to guess an option, you will guess B, C, or D. In that also, I feel that if this is not correct, I mean, this will also not be correct, because that confusion they would have created if somebody would have calculated 20. But since it is not negative 20, I think it will not be even positive 20. I think it will be B or C. This is just my tukka strategy. If I had to guess for no logical reason, there is no logic in it. It's just a guess, calculated guess, I would say. Shreyas sir's guessing. Yeah. Anyways, we'll see whether it is correct or wrong. So first of all, from C to A, there is no work done. I don't know whether you saw that, because it is a isochoric process. So work done will be 0 because it is isochoric process. Here to here, definitely work is done, but it will be negative in nature because it is isobaric in nature. So this is isobaric process. So the work done will be negative. Height into base, it's just this much area which you need to count. So height is 10 units, base is 2 units, so minus 20. This is SI units, this is also SI units, so minus 20 joules. Perfect. Everyone till this point, let me know, minus 20. Pakka? Very good. Now the only thing remaining is this part, right? This part. This part, what kind of process is this? PV raised to something is a constant. It is nothing but a polytropic process, guys. Polytropic process. Directly the work done formula is there. So work done for our polytropic process is NR final minus initial by 1 minus that polytropic power. So NR temperature is there, moles is there. Okay, let's see what we can do now. Okay, N R Uh, oh, delta T, I don't know how to calculate. So I can do one thing though. This I can write it as delta PV. Delta PV. Yes, that will be better. That means NRT2 was P2 V2. NRT1 will be P1 V1. That will be better. Upon 1 minus X. Here, this number 3 is basically your X. PV raised to X is constant. So definitely X is your number 3. Okay. So what is pressure 2 and volume 2? Pressure 2 is 10, volume 2 is 4. So this will be 10 multiplied by 4 minus pressure 1 is 20 and 2. This is so 20 and 2 upon 1 minus 3 is minus 2. So this will be 40 and this is also 40. Something is wrong unless the values given over here are itself wrong. For path A to B, I think the values given over here are wrong, guys, or else it should have worked. Yes, pressure was 10. Okay, something is wrong over here. Yeah, or else it should have worked. Or else it should definitely have, uh, yeah, worked. Or else something is wrong over here. Hmm. I'll tell you what is wrong. Actually, the question is fine only. The problem happened, where? Here. Check this out. Real gas. This is the problem. It's not an ideal gas. It's not an ideal gas, it's a real gas. So we have to redo everything. This formula will not work because this formula is only for ideal gases. How many of you saw that catch coming in? Such a small word. Yes, the real gas, guys. It's a real gas. So we cannot use these standard formulas. Oh, so you have to go by the basics. So, like, sir, what is a basic then? The basic is work done always is PdV. That always works. So somehow write pressure in terms of something else. And from here, we can see clearly pressure is RT multiplied by 1 by V cube, RT by V cube. But temperature is 27 degrees Celsius, which is 300 Kelvin. So I can put 300 R and volume I can take it on the top. Volume I can take it on the top. How many of you saw that? Isn't it a brilliant thing? So instead of pressure, put it as 300 times R, volume raised to minus 3, of course, and put over here integration of dV. Now this seems to be fine. This is perfectly fine, guys. Yep. And the initial volume and final volume will be 2 and 4. This is your initial volume and this is obviously your final volume. So 2 and 4 will be the limits. So 300 R is constant. It comes outside. V raised to minus 3 is integration is minus 2 by minus 2. So V raised to minus 2 by minus 2 limits 2 and 4, of course, 2 and 4. So 300 minus 2, I'll take out common. So first put 4. So 1 by 4 square minus, then put 2. So 2 square. So that will be minus 150. And this will be 1 by 16 minus 1 by 4. So this will be minus 150. And 16 is the LCM. So 1 minus 4, I believe. So which is minus 3. So minus 150 multiplied by minus 3 divided by 16. Minus minus positive. 15 threes are 45. So 450 divided by 16 joules. 450 divided by 16 joules. Is that clear, everyone? Just check it out. Yes. Awesome. 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 Great. Very good. Okay. Now, what is next? What is next? What is next? Check everything is fine. 1 minus 4. Yeah. 3. 3, 150, 16. Okay. Yes. So what is next? You just have to add them. Okay. So add minus 20 and 450 by 16. Just add both of them, guys. Just add both of them. Sir, can I have a decent placement if I have a degree in BS Data Science conducted by IIT Madras? No, no, no. You cannot expect. What do you mean by decent placement? That is a very vague word. If you can tell me a range, then probably I can tell you. But other than that, yeah, it's going to be difficult. Yeah. Come on, guys. Tell me what is the answer. Here, by the way, R was missing. Yeah. R, I forgot. So into R will be there everywhere. So sorry. Into R. So the total work done, let's calculate it. So the total work done will be 450 divided by 16R, and there will be a negative work of 20 joules. See now how much is this coming out to be. See now, yeah, I left out R, I just added up. Yes. Approximately, how much does it come out to be? Approximately, you'll get the answer, of course. So try to see whichever is the closest answer to that. Try to see whichever is the closest answer to that. Close enough answer, guys, is enough. Close enough answer. Is it 205? Just check it out. Yep, option B. Close enough to 205 joules. Very good. Very good. Excellent. 20 lakhs plus LPA. No, it's not so easy for a fresher. Just using online degree, no. Yeah, 20 lakhs plus LPA, guys. I mean, that is the average package for all IITians or even BITSians, even the top NITians. Okay, the top NIT is the average package, average I'm talking. So you are saying through a not so, it's not a entrance test based course. It's just a certificate course. So certificate courses, fresher fresher jobs are very, very difficult to get. Okay. All right. Fine. Next, let's go to some specific heat capacity based questions. An ideal gas at zero temperature is compressed to 1/4 of its volume. The ratio of specific heat at constant pressure to that of constant volume is 3/2. The change in the temperature is how much? So basically, when they tell you separately, CP and CV ratio is 3/2. What they are exactly trying to tell you is gamma is 3/2. Okay. The compressed to 1/4 of its final volume. So V2 is V1 by 4. Okay. Initial temperature is also given 273 Kelvin. So they have asked what is the change in the temperature. So obviously we need the final temperature. Is there a formula for adiabatic process specifically? Yeah, is there a suddenly means it is basically adiabatic process. Adiabatic process, sudden processes. So for that, temperature into volume raised to gamma minus 1 is a constant. That is the formula. TV raised to gamma minus 1 is a constant. So what is temperature 1? It is 273. Volume 1. Gamma is 3/2 minus 1 here. Final temperature, I do not know. Final volume, I will put V2 into gamma, which is 3/2 minus 1. Okay. So start solving this. 273. This will be V1. 3/2 minus 1 is 1/2. This will be T2. Volume 2 is V1 by 4. So V1 by 4 again raised to 1/2. Okay. So therefore T2 will be equal to 273 is there. V1 got cancelled. 4 goes on the top. Check this out. 4 goes on the top. Whole raised to 1/2. Now raised to 1/2 means how much? Root of 4, which is basically 2, guys. Yep. Basically, it is 2 times of 273. So if this is T2, if this is T2, how much will be delta T, which will be T2 minus T1, which is 2 into 273 minus 273. So it will be just 273 Kelvin. Yes, it will just be 273 Kelvin. Is that clear, my dear students? Yes, correct answer is 273. Very good. So final temperature, we did not have to find. We just had to find the change in the temperature. So that's the reason why we did this. Let's go to the next question on your screen. If you take a diatomic gas where gamma 1 is Cp by Cv for rigid molecule, gamma 2 is Cp by Cv for another diatomic molecule, but having vibrational degrees of freedom, which of the following is going to be correct? This is direct, guys. Come on. Everybody should be able to do it. If you take a rigid molecule, then there will be 3 translational, 2 rotational, which will make it 5 degrees of freedom. If you take another diatomic but also having vibration, then you will have 3 translational, 2 rotation and 2 vibration, which will make it 7 degrees of freedom. Now we all know gamma is 1 plus 2 by your degrees of freedom. So if a gas has more degrees of freedom, that means the gamma value will be less. So this has more degrees, so gamma will be less over here, and this has less degrees, so gamma will be more over here. So gamma 1 will be more than your gamma 2. Gamma 1 will be more than gamma 2, which is option A. Yep. Is that clear? Welcome, Viva. Welcome all the new students as well. Yep. Very good. Excellent. Let's go to the next question, guys, coming up on your screen. Okay, here it is. There is a mixture of 1 mole of mono, 1 mole of dia, ratio of heat capacities at constant volume of heat capacities of the gases at constant volume will be, I think, ratio of constant to pressure and constant volume. I think they have missed that question. I think it was supposed to be Cp by Cv. Okay, so basically you have to find Cp for the mixture and Cv for the mixture, and maybe we'll try to take the ratio of both of them. The formula goes like this. Whenever you have to find the Cp of a mixture, it is number of moles of the first gas, Cp of the first gas, second gas, contribution, the whole thing by N1 plus N2, just like the center of mass formula. If you notice, it's a monoatomic gas, 1 mole, so N1 is 1. Cp for a mono is 3R by 2, 5R by 2. Yeah. So Cp will be 5R by 2. Second diatomic gas is also 1 mole. Diatomic gas Cp will be 7R by 2. So I'll put 7R by 2 over here upon the total moles, which is 1 plus 1. So 5 plus 7 is nothing but 12. So it will be 12R by 2. Whole thing divided by 2, which is 12R by 2 2s are 4. So 12 by 4 is 3. So this will be basically 3R. This will be basically 3R. That is the Cp of the mixture. Everyone with me? Everybody with me? Very good. Excellent. Next. If you have to find Cv of the mixture, what will you do? Cp and Cv, they are related to each other. Cp minus Cv is equal to R. So Cv will be Cp minus R. So therefore, it will be 3R minus R, which will be basically 2R. So if gamma was asked, which will be Cp of the mixture by Cv of the mixture. So this will be nothing but 3R divided by 2R, which will be 3 by 2. So then it will be 3 by 2, which is option A. But as per the question that they have asked, the ratio of specific heat capacities of both the gases they have asked. So what they have asked, that particular ratio, what I think they have asked is Cv of first gas by Cv of the second gas. If that is what they have asked, then the first gas monoatomic Cv will be 3R by 2. The second gas is a diatomic, which is having 5R by 2. R 2 cancels, so then it will be 3 by 5, which is B option. Yeah, then it will be B option. Is that okay? Everybody with me? Yeah. I hope this is absolutely clear. Perfect. So I have solved both the questions actually. If they have asked just the ratio of the specific heat capacities, that is a laddu question. I mean, that should not be even a JEE question. I mean, what is that? Like CV upon CV. It's not even a good level question. So if a mixture of the gases gamma is asked, then you find CP separate, CV separate, then you find gamma of the mixture. To find CP or CV, use this center of mass kind of looking formula. Okay, let's go to the next question coming up on your screen. See this again, one more question is there. 2 moles of mono is mixed with 6 moles of dia. Can you find the mixture's molar specific heat capacity? The mixture's molar specific heat capacity. So they have asked at constant volume. So CV of the mixture they have asked, which is N1 CV1 plus N2 CV2, whole thing divided by N1 plus N2. So first time 2 moles. What kind? Mono. Mono means 3R by 2. Second, 6 moles. So 6 into. Dia means 5R by 2. Whole thing divided by 2 plus 6. Of course. 2 cancels. So it will just become 3R. 6 by 2 is 3. 3 5s are 15. So 15R. Whole thing divided by 8. So 15 plus 3 is nothing but 18R by 8. So divide by 2, it is 9R by 4. So 9R by 4 is option D, I believe. Yes, that is the correct answer. Then it was very straightforward. Correct. Very good. Okay, so we have come to the end of the class. We have practiced enough number of questions of KTG Thermo. This should 100% make your knowledge pakka for this particular topics. I've also given you the theory notes, the discussion of the concepts, the formulas, whatever graphs were involved. All models of question which came in January we have done. We have also done some previous year papers questions, so that in case any other question comes which was not asked in January, you should still be able to do it. Okay. So do not forget to leave a comment. I'm seeing what you guys are doing. Yep. And smash that like button right away right now. Tell all your classmates, Captain Shreyas sir, with the entire team, full serious preparation going on the Vedantu JEE English channel for your April attempt based on the NTA revenge pattern, which very few channels are doing, guys. So make sure you are aligned, you are staying tuned on the Vedantu JEE English channel. Okay. Thank you so much, guys. Bye bye. Take care. Have a great afternoon. See you again.